Okay, the next thing I'm going to talk about is the Norton equivalent circuit. It's very similar to what we have for the Thevenin, but just a little bit different in the arrangement. Um, the idea is very same as the Thevenin, is that if you have a circuit that composed of some resistance and um, some sources, and then we know there are two terminal coming out of that. If this is the one, in the Thevenin, what we will do that we will say that we want to replace that with a single um, battery and then a single resistance like that. This is what we wanted to do in the Thevenin. So it says that if this is going to be the EF, we want to replace it with the same EF that if we replace it with single battery and single resistance, it's going to behave the same. And this is what we use it. And this was what we have here was the Thevenin uh, circuit. The Norton circuit is very similar to this. Instead of replacing it with the battery and the resistor, we would go ahead and say we want to replace it with the single source, which I call here the IN. So single current source and a single resistance, but this time the resistance is in parallel with the source compared to what we had in the Thevenin. And then we have that two terminal coming out of that. So, and it's going to have the same, I would say, the resistance here. So this one is called Norton equivalent. So it's going to be Norton. Look at these two here. Both they have the same resistance. So the resistance in them is going to be the same. The only difference is that here the resistance is in series with the battery. Here in the Norton, the resistance is in parallel with the sources. And then it's going to be, again, the same as E and F. So if you are told, if you are given a circuit and they said, replace it with the Thevenin, this is how we are going to do. If they said that replace it with the Norton, this is what we are going to do. Basically, we are going to use this method to this configuration to replace that. One point that you want to look at it, remember that the IN, when we want to find the IN, to find the RT is very the same as how we find the RT here. So however we find the RT here, we will find the RT here as well. The only difference is how to find the IN, the value of IN. So look at here, if I short circuit this, here, and it's gonna gives me the IS. See, if I short circuit this here, and it's gonna gives me the ISC. Because I short circuit this resistance, the current through that resistance becomes zero. Nothing goes through that resistance. Therefore, the IN here, you will see the IN is going to be equal to ISC. So if I short circuit here in the original circuit and find the ISC, whatever value I have for the ISC is going to be the IN here. Remember, for the Thevenin, I used the VOC. Whatever is the VOC between E and F is going to be the VT here. It was what we had in, so we would say the VT is just the VOC, with the difference between these two. The same as here, the ISC, the I in this Norton circuit, the IN is the same as ISC here. So if I go ahead in the original circuit, just connect these two N together, whatever value I find for the ISC is exactly the value I'm going to use for IN in this circuit. And and for the R, again, the easiest way is that if you don't have any dependent sources in the original circuit, if you don't have any dependent source, just zero all the sources, and when you zero all the sources, find the equivalent of the remaining circuit is your RT, as we did it for the Thevenin. Is the same here. Okay, let's look at an example to see how we can solve and replace a circuit with a Norton equivalent. So here, assume I have a circuit like this. Sorry, goes down. And the current in that is Vx over 4. And then I go here and I have resistance here. I have a battery here. So it's going to 20. So it's going to be R1. It's going to be 20 ohm. And it's going to be 15 volts. And then go ahead and I have 2 resistance here. So R2 is a 15 ohm. And then I have the R3. It is going to be 5 ohm. And the voltage in that is going to be the Vx, is that one that actually affects this. And then I have these 2, and that's going to be and my 2 terminals coming out. So I want to replace this one with this time with the Norton equivalent. Again, to make it easier to figure out what's happening is that, so if I call this again E and F, and then I call this A, B, and call this one C and D. If you look at that again, I can go and put the B and D on top of each other. I put A and C on top of each other because there's only a wire between them. So it's going to make it easier to figure out what's going on. So I would redraw that again, this circuit. So it's going to be Vx divided by 4. And this time I just put this B and D on top of each other and I call it B. And then I have this resistance. So it's going to be R1. And then they have the battery is going to be 15 volt. And then I have that node A and C, which is just going to be the A. So I put A and C on top of each other as well. The same I'm going to have here is going to be two other resistance. So it's going to be R2. And this one is going to be R3. And it's going to be positive, negative. So, and then I have the E and F here. It's going to be my E, F, so it's going to be my terminal. And then I want to replace it with the Norton. Basically, I want to go ahead and say, okay, I want to replace this with a single current source. That's going to be IN, and a single resistance. It's going to be the RT. And then I'm going to have that two terminal here, E and F. So basically, I want to replace this circuit with these two elements in a way that whatever EF behave here is going to behave exactly the same here as well. So again, if you look at here, whatever happened in the E is going to happen in the B, and whatever happened in the F is going to happen in the A. So again, I'm going to choose the, I use the node voltage method. I'm going to choose the reference, and I choose the point A to be my reference here again. So it's going to be my reference node again. So the voltage at the A is going to be 0. The same, the voltage at the F is going to be 0 in this condition. The difference between E and F is the VOC. And this the difference between E and F is going to be the difference, the same as the difference between B and A. So because A is 0, so here the voltage at B is become VOC. And now if I go ahead and write the KCL at B, it's a node voltage. So if I write the KCL at B, would stay with the sigma I should be 0. So if I look at here the I look at the I that I have here, so I know that in this one, this is the current go there, then there's a current go here, and then the current go here. So I'm gonna just name, so it's gonna be, the one goes here is gonna be Vx divided by 4. This one, I'm gonna just call it I B toward A. So I B toward A1, and this one I goes from B toward A2, and then I would and there's nothing else going on there. So if I go ahead and say I add them together, it should come as 0. So I have Vx over 4 leaving, plus I goes from BA toward this one, IBA1 goes there. Again, look at here. If I come here and look at this, if I look at this node here, and if you look at this node here between this is connected to the battery, and the battery connected to the reference. So one end of the battery is to the reference, the other end is connected to this node. So this node has the same voltage as the battery. So it's going to be the voltage here, and assume it's going to be point again G. So the V at G is going to be 15 volt, plus 15 volt, because it's connected to the positive part of that voltage. So here the current goes from B toward A is basically, I can say, is the same as the one is goes from B toward G. So the one that goes from B to G is VB minus VG divided by R1. And then here and I'm going to just replace them with the values. Then again here, the one that goes through this leg, so IB2, so it's going to be VB minus VA divided by the resistance between them. So there are two resistance between them, and they are in series, so I can add them together. So it's going to be R2 plus R3, because I can replace these two with a single one. So they are in series, so I can add them together. So it's going to be Z comes 0. Now if we go and replace these values, so I'm going to have the Vx divided by 4 plus the Vb is the VOC. I know the voltage at V is the VOC. And the V at G is the 15. And R1 is 20 ohm. Plus the V at V again is the VOC. And V at A is 0. So minus 0. And then the R2 plus R1 is going to be 15 plus 5. So R2 is 15, R3 is 5. And then it becomes 0. So it's our first equation that we have, and it has the VOC and Vx. So we have one equation, and we have two unknowns in this case that we have. Now we have to find another equation in order to solve it, solve this problem. Now here, so if you look at here, this voltage is Vx. The voltage is Vx and goes from the voltage at two ends is VOC. So if I look at this this one, B and A, from here to here, the voltage from point B toward A is VOC is going to be divided between the voltage in R2 and the voltage in R3. Basically, the voltage divider method. So what the voltage you have is going to be divided between these two. Remember, so I'm going to just put it here, very simple format. So I assume I have something like that. Then I have two resistors. Remember when we're talking about the voltage resistance was that if I have a battery and then I have two resistance or a couple of resistance in series, then the voltage would be divided between them. As long as I have a couple of resistance in series and the both end, I know the voltage as both ends, the voltage in both ends is going to be divided between those resistance based on the value of the value of their resistance. So here, if I write the voltage divided method, for B toward A, I know that the the Vx. If I want to find the Vx is the resistance at the that. So it's going to be R3 divided by R2 plus R3 times the total voltage in between them, which the total voltage between B and A is going to be VOC. So basically, it's going to tell me the Vx is going to be R3, which is going to be 5 ohm, divided by 15 plus 5 times VOC. So if you solve these two equations together, solve these two sets of equations together, it's going to tell you the VOC would comes out as a 4.62 volt. So it's going to, this is the voltage we are going to have at that point. So now that we have the voltage there, then the next thing that we need to find is going to be the current goes through the E and F. If we go ahead and short circuit the system, so you see what's happening there. So if I go ahead and short circuit the system, it means that if I go and connect this wire from here to here and make it ISC. So this is the ISC go through that wire. So look at, if I connect the E and F, what's happening is going to short circuit B and A. So basically there is no current is going through this wire here. So the current through this wire becomes 0. Because the current through this wire becomes 0, so no current goes through that second resistance as well, the third resistance, the R3 as well. So the voltage in that resistance will become 0 as well. So it would become 0 as well, because there's nothing goes in there. If this becomes 0, then this will become 0 as well. So this one would be also 0. Put it there. So this also becomes 0, because the Vx is going to be 0. So the only thing is going to left is this line. So basically I can remove these two. I can remove this wire here and I can remove this wire here, because there's nothing going in there. So only one is going to left is going from C, D, E, F back to C. That's the circuit I'm going to have in that case. So here, if I have only this one, if all the current goes through the R1, so it's connected to the battery. So it's basically is one resistance connected to one battery. That's all I have in this one. So oops. So basically, if I do the ISC, what is I'm gonna left here, just there's nothing going there. So I draw it very small here, and then you have the R2 here, and then you have the battery here, the 15 volt, and then there's nothing go in this part as well, and then you have this EF at the very end. So it's something that you have is going to be look like this. So you have point D, point E, F, and C. So this is the circuit that we have, and that one is has only one battery, 15 volt, and then the 20 resistance. So if I write the V is IR, what I have here, the V is 15 volt, and the I is the same as ISC, because if this the ISC goes here, this the ISC go all the way through that. There's no other I. So the I is going to be the ISC. And then you have the R, which is going to be, sorry, it's going to be R1, not R2. So it's R1. So it's the R1, which is going to be the 20 volt. So and then the ISC here from this equation would become at the 0.75 amp. So it's going to be the ISC goes through that wire. And we know from the previously from the Thevenin, we know that we know the VOC, we know the ISC here. So we know the RT, or basically what we know is that the VOC, or VOC is ISC times RT. From the Thevenin, we know that equation. So then the RT is going to be the VOC, which is going to be the 4.62 divided by the ISC, which is at 0.75. And then the arc is going to be 6.15. Oh, so this equation is from the Thevenin. We know it from the Thevenin. We know that part from the Thevenin. So the RT here, we know that the RT is going to be, therefore it's going to be, and the RT in the Thevenin is the same as the RT in the Norton. So it's going to be 6.50. So this is the RT we have. And the IN, remember the IN is the same as the ISC. So the IN is exactly ISC. Oh, sorry. Is ISC, and it is going to be 0.75 amp. And this is how we are going to get the equivalent, the Norton equivalent of this circuit.